to us about these security risks of Python packaging. All yours.
Thank you. Welcome everyone. Thank you. So first of all, let me say thanks to the organizers of PyTexas. Really awesome conference, and really looking forward to the rest of this conference we have here today. All right, so let's talk about why installing Python packages is still a security risk. So many of you have probably heard this phrase before. Maybe somebody has told you, do not install untrusted packages. I say this to my colleagues all the time. You've probably had someone else tell you the same. In this talk, what I want to do is really help you understand why you should not install untrusted packages and really see the mechanisms in Python packaging and the actual malware that can be deployed through Python packages. So hopefully from this talk, you'll come away both understanding what can go wrong and some practical techniques you can use to help mitigate these challenges. All right, so what are the risks of Python package installation? Well, it all comes down to arbitrary code execution. That's the #1 risk. Now, you hear about a lot of other bad things that happen from Python packages, but those bad things are after arbitrary code execution. Furthermore, your privileges are enough. When you install packages, the process has your privileges. That's enough to do real harm. You don't have to be root to do real harm, and that's why package threats are so significant. When we install packages, those packages have dependencies, and those dependencies have dependencies. We call those transitive dependencies. And those transitive dependencies all carry the same risk as your original package, but often go unnoticed. And that increases the complexity and dangers of package installation. All right, so there's two main vectors of package attacks. Now, importing a module is running somebody else's code, and when we run somebody else's code, we always take on risk. So it's expected that when you run somebody else's code, you are under some risk. But there's two more unexpected vectors. The first is at installation time. Under various scenarios, still under installation time, setup.py will be run, and that leads to potentials of malicious code being run on your system. Secondary and less well known is at interpreter start time. Using a bundle of routines that happen under site.main, and we'll explain this, a number of things can happen that at interpreter start time can execute malware, and we'll see how these work as we go on. All right, so how do package-based attacks begin? Well, a very common one, and one very popular very recently, are compromised maintainer credentials. Compromised PyPI creds, compromised GitHub accounts have been well-known attack vectors that have been used to compromise packages. Once a package is compromised, malicious code can be injected, malicious dependencies can be added. The code might operate and look exactly like it used to, but it might just have a malicious dependency. And in the last couple of weeks, you may have heard of the Axios JavaScript library attack, which used this very technique. In masquerading, you've probably heard about. Requests and Colorama are common targets. Masquerading is when a package doesn't use typo squatting, but looks legitimate, but is not. And a recent example of that is a package called Grok Wrapper, which was not an official Grok Wrapper. Dependency confusion is when a legitimate package is installed in PyPI to mock or simulate an internal package, a package that might be hosted internally or on a public forum, but not on PyPI. In this case, the package management system will go and try to pull it first from PyPI and not from the intended source. And Torch Triton from the PyTorch community was a recent case where this very thing happened. Social engineering remains an ongoing and persistent threat. Fake recruiters, fake IT support are well-known cases of where people have pretended to be someone they're not and encourage you to install a package either for a fake interview, as part of a fake recruitment process, or as part of fake IT support, and there you get malware on your system. So what we're doing here, what these attacks are all about, is attacking the supply chain. And the reason attacking the supply chain is so valuable is it has huge opportunity for spread. By attacking popular packages, you can get malware in personal machines, in large organizations, in machines in governments, and other places. So it's a tremendous opportunity. PyPI, NPM, crates.io are all open ecosystems, and they need to be. We love it that they are open ecosystems, but that inherently makes them vulnerable to malware. And running code, like it or not, is common at installation. And that's where a lot of these threats come from. Python, as I've already mentioned, has setup.py. In JavaScript, we have various scripts that run on installation, like post install. And even Rust, our bastion of safety, has build.rs, which is a file that will be compiled and run as part of compiling a Rust package, which is very unfortunate. All right, supply chain attacks are increasing, and with prevalence of AI coding, they're just going to keep on coming. Just do some recent searches, and you will see countless attacks in the news, some really notable ones recently, Light LLM, the Axios one purportedly by North Korean actors. It goes on, and even Rust has got some malware in crates.io. So this is not going away. This is a prevalent problem, and we need to be vigilant. So why do I care? Well, in my organization, I oversee, to some extent, the cybersecurity, and in looking at all the controls we have in place, I kept on coming back to the supply chain and my developers' machines as being a consistent source of risk. Furthermore, I recognize that of the controls that are out there, none of them are truly foolproof, and we'll see some examples of these as we go. This led me to develop a system-wide Python vulnerability scanner I called Fetter, which allows you to scan an entire system to find all packages on a system and any vulnerabilities there. We'll talk a little bit more about that later on. So why should you care? Well, you are a gateway into your organization. Whether that organization is your business, your community, your open source projects, if something lands on your machine, it can compromise your organization. Even if not, credentials and API key theft can cause real problems. And with many of us having AI API keys on our systems now that can bill up significant amounts of expenses if abused, this is something that we always need to be concerned about. And you should care because there are a number of practical mitigations available. All right, so now let's dive into the mechanisms of Python malware. I want to show you what malware actually looks like. And not, of course, so you can use it, but so you can see how easy it is to do. Python makes malware really, really easy. You generally need one line of code, maybe with a few semicolons, and the standard library has everything we need. You don't need complicated dependencies to write Python malware. Everything you need is right there. So common malware tactics, we'll see some examples of these include reconnaissance, credential exfiltration. There we're going to steal SSH keys, AWS tokens, API keys, environment variables, .env files. Clipboard extraction is great for getting cryptocurrency wallet addresses and other secrets. Data theft is a common attack. Persistence techniques might try to capture your credentials or install backdoors so the attacker can come back later. Resource abuse, like crypto miners and botnets, want to use your CPU and resources to do bad things. And then finally, ransomware or wiper attacks make your machine completely inoperable. But let's look at a few examples. So reconnaissance. In reconnaissance situation, an attacker lands on your machine and they want to learn about you. They want to know what kind of target they found. And we can do something like this in Python very simply. We import a few things. We get the socket host name, we get the login, we get the platform, we get the current working directory, and then we just package that up and send that to a domain of our choosing. I can tie these all together with semicolons, and this is one line that exfiltrates some valuable information about where my malware landed. Environment variable exfiltration, as I mentioned, is a common approach. Again, Python makes this extremely easy. os.environ will return to you a mapping of all of your environment variables in the current process. We can wrap that up in a dictionary, URL encode it, and then pass it on to a domain of our choosing. Clipboard exfiltration, as I mentioned, well, you can do that out of the box in Python still, because Python still ships with tk-enter, and tk-enter has a way to get clipboard contents. So there again, we can grab the contents of the clipboard and then send it off. Now, if we happen to land on a Linux box, we can do some more fun things. And of course, attackers can make platform-specific adjustments. But if we land on a Linux box, we can, for example, exfiltrate the shell history every hour. We do that by calling out to os.system, launching a nohup bash. Nohup is short for no hangup, an ancient Linux command that allows us to have a process that continues as long as possible. And this will, in a bash loop, extract the user's bash history and send it off to a domain every hour. You can get a lot of information from someone's bash history. Most dangerous is something like this, a reverse shell. So with something like this, we're using OS to get the user's bash RC and then appending a single line to that bash RC. That single line is going to launch a shell. Every time I open a new terminal, every time I start a new process, this is going to launch another bash process that is going to create a reverse shell to a domain, whatever domain I want. This allows bidirectional, full user-level control of your system. This is bad news. And it's just a few lines of code. All right, so now hopefully you're a little worried about the things that are out there, and you should be. But let's step aside and look at the history of Python packaging and kind of look at how the opportunities for some of these things got into Python. Now, of course, as I pointed out, all open source packages have some danger of malware being distributed via packaging, but we're going to focus on Python. So the two things we're concerned about is why does setup.py exist, and do we still need it? And what does site.main actually do? So first, setup.py. Setup.py first came around 26 years ago in PEP 229, which established setup.py actually originally as a way of making C extension compilation more portable, but also brought along the convention of calling Python setup.py install as a way of installing a package into the user's site packages. Many of us who have used Python for a long time remember this as the main way we used to install things before we had pip. So setup.py continues to be where metadata for a package is defined all the way until 2020. So for all that time, that is where metadata was defined. And running that setup.py is required for source installations all the way to 2020. Now, I say source installations because in 2012, we got the wheel. The wheel format is a binary package format that allows us to package the contents of a package in a way that doesn't require running setup.py. Pip supported that in 2013, and at that point, finally, we could install things without running setup.py, which is great. We still have plenty of other risks. So declarative metadata is the answer to putting metadata in a runnable Python script, and thus we can get metadata without arbitrary code execution. So PEP 5.18 in 2016 introduced pyproject.toml, but interestingly, it wasn't initially for metadata. It was initially to allow users to define their own build systems. It took a couple more years in 2020 to put metadata in pyproject.toml. So 2020, really an important year for Python packaging. Now, source installations no longer require running setup.py. You don't even need a setup.py in your Python package, except for a few special cases. Okay, so we talked about setup.py. Now I want to talk about this site.main thing that I've been talking about, which might be the most novel to many of you. Way back in Python 1.5, that's 1.5, site.py was added to the Python library, and this created site packages as the place to install packages. And that site packages directory was automatically added to sys.path, the list of directories Python searches to find your packages. A curious addition was the introduction of these .pth files. These .pth files were just text files, but would allow bulk additions to the search path of sys.path. So if you wanted Python to find packages elsewhere, you could put those paths in sys.path, and put that .pth file in your site packages, and then Python would automatically add those paths to the search path. It also permitted site customize.py, which is a file that can live in site packages that is also run on site initialization. Now, recognizing that these things were heavy, Python introduced a way to not run these things at startup, and that's Python-big S, which is a very useful thing. Now, a few years later, in 2003, an extension was made to the processing of PTH files such that if the line starts with import, that whole line is called with exec. Let me say that again. This used to be just a file with file paths. Then what was added was the ability to run arbitrary code as one line. And as you all know, with semicolons, that can be as much code as you want, essentially, can be packaged into a PTH file and run at system startup. A few more additions came with the evolution of site packages until we get them in virtual environments. But site.main is really the thing we want to think about. This is called by default at interpreter startup. Whenever you start Python, site.main is being called. Of course, you can avoid it with -big S, but many of us don't do that. This reads all PTH files, it adds them to sys.path, it calls exec on all of those lines that start with import, and PTH files are installable from both wheels and setup.py. Also, site.main imports site customized and user customized.py, which can also be installed from wheels and setup.py, and are also other ways that arbitrary code execution can happen on your machine. A curious detail is that if any of these questionable things raise exceptions, they will not fail. The exceptions are non-terminal. They're caught and printed out, and won't even fail your startup, which I would argue is still a very questionable practice. Okay, so how do we get malware in our packages, even in the current day, with everything that we've changed? Well, we see continued abuse of setup.py, and we have it for a number of reasons. Many C extensions still require using setup.py if they're using setup tools. And just legacy. Of the top 1,000 downloaded packages, 454 still have setup.py. Many of them may not actually need it anymore. The other common approach, as we'll see, is planting code in site packages, and we've talked about some of the approaches we can do there. We can do that with PTH files, we can do that with site customize and user customize. So let's look at what some of the packaging controls look like and how they would carry malware. So if we have a Python package that builds C extensions and we are using setup tools, the basic default, we need to define our extension modules in setup.py. We can have a pyproject.toml, but we still need a setup.py. So say I have a C extension that has this very nice pyproject.toml, looks very clean, nothing could be wrong there, but then I have to have a setup.py that has a setup function that defines the extensions, and in that extensions block, I can stick some arbitrary code that can be tucked away to do whatever I want. In my setup.py, I could also install a PTH file, which again would give me arbitrary code access soon after the interpreter starts. So we can do this by simply having a nice setup.py function and then define a command class. The command class lets us overload what build_py does, and there we can see we can subclass that and re-implement run to do what it normally does, but then also write a malicious PTH file. Now, native pyproject.toml files, those with the setup tools backend, cannot install PTH files on their own. Pyproject.toml is supposed to not really do that much dynamic stuff. But some backends permit specialized functionality. And one example is Hatch. So Hatch offers targets.wheel.forceInclude. Sounds a little suspicious. With that, we can take our pyproject.toml, and if we decide to use Hatchling as our backend, all we have to do is add one line to our pyproject.toml, which will allow us to inject a PTH file into site packages, gaining remote code execution on the system we're installing. Now, okay, maybe you're installing wheels, you're not too worried, you're not running setup.py. Well, wheels are just zip archives. And if an adversary gets access to that zip archive, they can unpack that zip archive and add a PTH file into that zip archive, properly update a few files, and then on installation, you will have a PTH file on your system. Now, this is detectable if you validate your hashes, which is why hash validation is so important. Okay, so we've seen that there's still quite a few ways to get malware on your system. What are some things you can do to mitigate this threat? So defending PyPI is an active area of mitigation, avoiding site.main, package screening, and deception technology. We'll look at each of these. So defending PyPI has been an active area of focus for the last quite a few years. One of the big initial steps was in 2023 when PyPI had its first safety and security engineer. It then established trusted publishing, enforcement of 2FA for all users in 2024, malware reporting conveniently located on package pages soon followed, automatic tools to prevent malicious zips, and typo squatting detection have all been added to PyPI, which is great. And I know the team there works really hard to improve this. But no control will completely remove malware from an open ecosystem like PyPI. Now, we also can choose to avoid site.main entirely. Again, this runs by default every time you start Python, which might be a reason for your slow startup time, by the way. If you call python-s, it will avoid running site.main, but then you can't import any of your packages. Well, an easy fix is to just get the site packages directory and add it to your sys.path. This gives you access to all of your packages, but doesn't run any of the code potentially lurking in PTH files, site customize, or other places. Now, there's many ways we can screen our packages. One of the most basic approaches is to use lock files with pinned requirements. If you do not use pinned requirements and someone tries to install your package, or you install your package on another system, you never know what version of a dependency you will get. So pinning your requirements and pinning all of your dependencies, not just your primary dependencies, but your transitive dependencies in a lock file is critical. And hopefully I've convinced you that actually doing hash validation is a good thing, because anybody can intercept a wheel file and inject malware in that wheel file. We can do some things to evaluate packages before we install. Which is basically saying kind of do a little research before you pip install. Somebody says, oh, have you seen this cool package? You should try it. Try to Google it first. Some resources like libraries.io and SNCC offer various rankings, source rank and package health scores. These are good to get a sense of if there's any potential issues about a package, but they are not foolproof for a number of reasons. A package may have transitive dependencies that offer other problems. And of course, there's a delay in vulnerability discovery. So again, we're not finding any foolproof solutions here. Another way of package screening is controlling the installable artifact. So a lot of big organizations, some of your own companies might use something like JFrog Artifactory or AWS Code Artifact. And by doing so, or having private PyPI instances, and we can set pip's index URL to force pip to only use a URL of our choosing, and in that URL we can carefully control what packages get in there. And that does give us some safety, but it is always circumventable. One of your users might just download a package and move it into site packages, or leave your network and find another way to get a package on their systems. So while somewhat effective, I think these also are quite circumventable. There's various vulnerability scanners out there that will look at your packages and tell you if they have known vulnerabilities. GitHub Dependabot, if you're not using it already, is awesome. I strongly encourage you to use it. It will isolate any vulnerabilities and packages in your code, and it will even give you pull requests to fix them from time to time. Pip Audit has been around for a long time, which will look at your requirements or pyproject.toml and tell you if there's any vulnerabilities in there. The tool I created called Fetter will scan your entire system for any Python vulnerabilities found in any site packages. But these, and furthermore, if you're working with agents, you might have found that your agents are a little unreliable in their package selection. I find it quite surprising, some of the versions I get from my agents. For that, I created the Fetter MCP. We learned about MCPs this morning. This is an MCP that is available for free. You can go grab it right there. This has a most recent not vulnerable tool that you can tell your agent to always use, such that you always get a recent but not a vulnerable package, which is probably what you want and may not be what your agent gives you. Again, this is only as good as known vulnerabilities, so it is not foolproof. Fetter also has a tool to inspect these runnable site files. This finds all PTH, site customized.py, and user customized.py files and shows you where they are and what's inside them. So this is a sampling from my machine that found every site packages directory on my system and every PTH or runnable site file and shows me a bit of the contents. Now, we can't see all the details in this little screen, but for example, to look at one, I imagine many of you will have this PTH file on your system. This is distutil's way of looking for an environment variable. If that environment variable is not found, it takes a certain action. But this code is lurking there and runs every time you start up Python. This code is fine. Some other code may not be. The last mitigation is one that I think is actually really quite cool. We know that much malware exfiltrates secrets. That's often what it's doing. So and we've seen that many of our approaches are not foolproof. So what we can do instead is lay traps. Canary Tokens is a great service that provides this for free. Right now, you can go to Canary Tokens and you can download a convincing decoy AWS credential or API key. You lay these things on your system in the appropriate places, and when users try to use them, you get a notification. So this doesn't stop attacks, but it gives you a very clear and powerful signal that something bad is happening. And deploying these organization-wide on all developer machines is something I would recommend. All right, so the easiest way to get malware on your machine is to install it yourself. You don't have to break all the security controls. You don't have to hack or brute force your password. You just have to put it there yourself. And that's why package threats are such an ongoing challenge. So in conclusion, as we started with, do not install untrusted packages. Lock and screen your packages. Avoid setup.py when you can. Always favor wheels. And really question what's going on in site.main. And finally, lay traps. Thank you very much.
Well, I can safely say that generated a lot of questions,
Okay.
a lot of interest. The first question, the first sentence, perfect. This scares me. How do I keep auditing all the packages? Are dev containers or Docker containers helpful to get rid of most of these kinds of attacks?
Yeah, it's true. Using containerized execution will help mitigate the blast radius, as we like to say, of malware. So that can help. That's not always practical for everything, but that can help a little bit. Though you might, in your Docker container, have a .env file, right? And that env file might have secrets that could be exfiltrated. So it's scary, and it's getting scarier all the time. So I'm sorry I don't have warm fuzzies to offer.
Well, you know, at least you left us with plenty of hope.
Yeah.
Would it make sense to flag in the PyPy UI project still using setup.py?
Yeah, something like that could be done. As I said, there seem to be there's a few corner cases that still need setup.py, but that's actually quite an interesting idea. Over the history of Python, there's been kind of these push campaigns to get people to do things. When wheels first came out, there was a push campaign to get everybody to start shipping wheels, and a big list of all the packages that hadn't yet moved to wheels. So I think that is actually a worthwhile consideration.
Yeah. On that note, the next question. Setup.py just runs at build time, right? You kind of touched on this, but pip installing won't run that arbitrary code on your machine there unless you're building it, right?
Source, if you're installing a wheel, setup.py is not called. So wheels are good for that. But if you happen to have a source installation, if you look at some of the malware that's come out, they don't publish wheels, they just publish tar.gz. Source installations still have to run setup.py.
Gotcha. How are companies like yours handling these kind of supply chain attacks? Like, are there any processes that help when team velocity around this stuff is at stake?
Team velocity is a real challenge. We do manual review, so I beseech all of my teams to submit packages for review before installing, but that is not foolproof. As I mentioned, the Feder tool that I've been working on, some extensions of that give me visibility to all the packages on all the systems across my organization, but that's still reactive and not a sufficient defense. So that laying traps is also a good thing. We have Canary tokens on all of our dev machines, which is another mitigation. So those are some things I would recommend.
Awesome. Well, there are plenty more questions. I think we're going to take the rest to Discord because we could be up here all day.
No problem.
But you've sufficiently terrified us. So
very good.
Thanks so much, Chris.
Thank you very much.